smaller and the channel lengths get smaller, we get a lot of non-ideal things. And there's a lot of them. I'm not going to go through them all. I'm just going to highlight some of the important ones. There's a thing called latchup can occur. That's when your transistors short circuit to each other in CMOS circuits. This comes about because, maybe I'll just use this slide. We back up here quite a ways. In this situation here, we have a CMOS circuit with a P and an N. There's a device in here called a thyristor. It has a P here, an N here, a P here, and an N here. So if we follow that path, we basically have this device. It looks like this. 1, 2, 3, 4. It goes P, N, P, N. Okay? And that's like an NPN transistor here and a PNP transistor. And then just under the right conditions, you can make them both turn on, and you can have current that goes from this node to this node. And normally this node is ground. That's the source of the NMOS. And this node is VDD, which is the power supply. And if those short circuit to each other, you get a whole bunch of current going through them. And in that situation, it's kind of destructive. It can actually blow up the chip. So we normally don't have to worry about it, but it's a thing that can exist. So that's called latchup. There's all kinds of threshold variations that can happen with these short channel devices. Again, I had a slide. All these things affect the threshold here. And so we can get all kinds of threshold variation that we have to deal with shorts, particularly with short channels. There's parasitic resistance, particularly as we shrink the devices down. These, do I have a picture of? I don't have a good picture here. Do I have a good picture? Yeah, for instance, you have to make a contact here, and this has to go into this P substrate or a contact here. Well, when we make the devices really small, we start getting a lot of resistance. These metal wires get really narrow and the contacts between them get narrow. So we get all kinds of parasitic resistance. That's another thing that becomes really important, particularly with really small devices. So we get parasitic resistance. We get subthreshold current. We kind of talked about this already. Let's go back here. Where are we at? When's the last one? Just to go over this again. Yeah, we had a transistor. We said, here's our NMOS transistor. This is P and N, and we had a gate. And we said, oh yeah, when this is turned off, there's no channel, right? And we had these diodes, reverse bias diodes. It kind of looks like this. And I said, yeah, when there's no channel, there's no conduction. But these diodes, we know, look like this, right? This is their forward current. And then the reverse current, I'm exaggerating here, but there's a small amount of current. So there is a small amount of leakage current that can go through this device. And this one's forward bias. It's like picoamps of current, but it's important. So there's this, we call this subthreshold because we haven't gone above the threshold voltage. We haven't turned the channel on, but there's still leakage through these reverse bias junctions. And so that kind of limits our minimum amount of current. That's a small amount of DC current. So that's important. It turns out that as we shrink the devices down, we have this equation for saturation. It looks like this, and we have this. I said this is VGS minus VT squared. Well, as we get smaller devices, this isn't necessarily squared. It can get smaller, getting closer to 1. So yeah, the transistors aren't given as much current as we'd like. And we also get things like velocity saturation, mobility degradation. There's a whole bunch of things that happen that, they basically make the transistors a little worse as we make them smaller and smaller. Yeah, we're not going to spend a lot of time on that. I just wanted you to be aware that they exist. Now we've got a couple more new slides I added. So let's just move this out of the way. So on the left here, we have classic lateral PNP transistor we're talking about. So if you look at this, here's our substrate. This is a P well in this case, but it could just barely be P substrate. Here's our N-type source and drain, and here's our gate. So the transistor is kind of going this way, right? Current would go this way for this transistor. So I've kind of switched it 90 degrees, but this is our gate. So that's a classic planar field effect transistor, okay, that we've been talking about. Well, it turns out as transistors channel lengths got smaller and smaller, it got hard to control this channel that was under the gate. So this little dashed box in here, that's the channel. And that channel, this dimension is the length, right? This is the length right here. As it got smaller and smaller, forming the channel underneath it, particularly turning it off, got harder and harder. So what people moved to what called FinFET. And this is a tri-gate. It has 3 gates. And in a FinFET, we still have a substrate. We have a P-well here. We have source and drain. But now the gate, which is this red material, it wraps all the way around. So the source and drain region became vertical. Here it's lateral, right? It's kind of lateral this way. So now the current is going in this direction. We're still going through this from source to drain, right? Or drain to source the other way. Current's going in that direction. But now the gate wraps around this fin, the transistor. You can kind of think about it. This source drain was kind of like it was a mound. It just sort of grew up. So now we have this mountain where the source drain sticks up, and the gate just wraps around that mountain. Turns out that gave us a lot better control of this channel. So now the channel, before the channel was like this dash, the channel now is this whole little 3-dimensional thing, right? That's wrapped around. So that's called FinFET transistors. So is the FinFET harder to manufacture? Yeah, the FinFET's a lot harder to manufacture, particularly because the device sizes are much smaller. When you go down below, I don't know, like 20 nanometers, it's all FinFET, okay? If you look at this slide we did back here, way back, yeah, right here. Down below 22 nanometers, 20 nanometers, this is all FinFET. All modern devices down 20 nanometers and below are FinFETs. Yeah, so that's kind of like the newest technology uses these FinFETs. And one of the things that came about, I already mentioned, is that now the PMOS and NMOS, they were able to adjust them so that they have basically the mobility of P holes and electrons is the same. And it kind of relates to the strain that's put in these devices. Moving ahead, even FinFETs have a problem in that controlling it. So the latest technology, well, right now people are working on 3 nanometer, and TSMC, which is one of the leaders, they're still doing FinFETs for 3 nanometer. But Intel and Samsung, I think, are moving to these other technologies, nanowires and nanosheets. And they kind of like FinFETs, except now the gate totally surrounds it. So it gives even better control of the channels through these devices. And it turns out nanowires are more efficient in terms of current, but nanosheets are easy to manufacture. And this is just a cross section of what a nanosheet looks like. So the gate is this kind of totally surrounds the source and drains. These aren't in production yet, but people are moving towards that direction. And we've got 2 minutes left. We got our last slide. I think this is the last slide. This slide on the bottom left here kind of shows, this is the channel thickness. So today we're out here at 5 nanometers, and probably this year we will get 3 nanometers. And people are moving down. This is the way technology is moving. We're reducing the channel thickness, right? Silicon is right here, these triangles. And what this is showing you on the left here, the y-axis, is the mobility of the carriers. Well, you can see silicon mobility. If I were to extend this off, it's been like this, but the silicon mobility is shrinking. And as we move below about 1 nanometer thickness, it drops off like a cliff. So we really can't make silicon transistors below about 1 nanometer. So people are really actively looking at, what other technologies can we use if we try to keep shrinking transistors down? And they're looking at all kinds of exotic materials. These black diamonds, that's carbon nanotubes. They keep their conductivity well down below 1 nanometer channel thickness. They're also looking at these, I don't know, WSC, all these kind of, I don't even know what they are. Selenium, I don't know what the W is. Tungsten, selenium, tungsten, I don't know. mobilium, selenium, I don't know, there's all kinds, or sulfur, I guess S is sulfur. But anyway, there's a lot of R&D going on these new types of materials. What are we going to do when we try to get down below 1 nanometer? Because we're getting there close. We're at 3 now. So the next node probably goes to 2 and then maybe 1, I don't know. But that's a big challenge. Okay, that's the end of this set of notes. So next Thursday, or this Thursday, we'll start the next lecture 2.